All right, so we're still in section 8.4. We're looking at the graphs of logarithmic functions. So I want to point out that when you have a logarithmic function, this f of x equals log base b of x, you can, again, you could have the function notation f of x, or you can have y equals. This right here, whatever the argument is, there is a stipulation that this has to be a positive real number. So that value that you put in has to be between 0 and positive infinity. It can't be 0 and it can't be negative infinity, or negative numbers, I'm sorry, to negative infinity. So if you were, and you'll notice if you take the calculator and you put in the log of 0, it will tell you there's an error. If you put in the log of a negative 5, it will tell you there's an error. So you have to be careful that this value, it comes from the positive real numbers. So the graph of a logarithmic function is defined by f of x is equal to log base b of x. And there's some stipulations on b. It's also a positive real number, and it can't be equal to 1. So filling in the blanks here, if b is greater than 1, then the function will be an increasing logarithmic function. And if b is between 0 and 1, then it is a decreasing logarithmic function. So if I take a look at the graphs of it, here is, this is when b is greater than 1, and you have an increasing function. And this one down here, this is when b is between 0 and 1, and you have what appears to be a decreasing function. Now, there's nothing, b cannot be below 0, so, or equal to 0, it's told to us right here. So there's no graph if those things were true. The range, well, the range of these logarithmic functions, if I take a look, when I'm looking for the range, remember we're looking at the y-axis. So on the y-axis, my points go to negative, they go all the way down here and they go up here. This is going to continue on this way forever, and it'll continue on that way. So for the range, it's all real numbers. It's the set of all real numbers, or written in interval notation, it would be from negative infinity to positive infinity. The domain, though, there is that stipulation that it can only be from 0 to infinity. The x value you can only put in from 0 to infinity, and it's shown here. You don't, when you look at the x-axis, I don't see any points over on this side. So only from above 0 is where the x values all lie. So you can say that's an interval notation, or in words it would be all positive real numbers. The line x equals 0, or this should say y-axis, is a vertical asymptote, meaning that this does not touch or cross, this graph does not touch or cross the y-axis. It gets closer and closer to it, but it never intersects it. And the last thing here is the function passes through the point 1, 0. And the reason why both of these functions are passing through that same point, because if you evaluated the log base b of 1, you always get 0. No matter what your base is, anything raised to the 0 power will equal 1. So that is going to be a point that's in common. So we're going to look at graphing some of these. So this one, when I look at this, I see a base of 3. I would expect, because the base is greater than 1, an increasing function. You have to choose some values to put in here. Now, I think what I'm going to do here is think of this in this respect. So this would, if I think about it in exponential notation, it might be easier. So this would be 3, and I'm going to say, instead of f of x, I'm going to say y is equal to x. So let's put in values for here. If you put in -1, you would get 1/3. If you put in an exponent of 0, you would get 1. If you put in an exponent of 1 for y, you would get 3. And if you put in an exponent of 2, you would get 9. So because I can't really I can't figure out the log base 3 of x, putting in values of x here, without putting it in this exponential form. So I can kind of work backwards also. So let's graph these and see where it would be. So we've got 1/3 -1. We've got 1 0, 3 1, and then 9 2, which would be somewhere right there. This is the type of graph that I will get. Now let's try the next one. Well, for the next one, I'm going to say 1/4 to the y power is equal to x. So 1/4 to some power is equal to x. So again, I'm going to put in some values. Now I'm picking values around the origin. That's where I would suggest to start. When you plug in -2 here for y, you're going to get 1 to the 16th power. I'm sorry. I did that wrong. You will get 1/4 to the -2nd power, which would give me 1/4 to the -2, which would be 4 squared, which is 16. If I plugged in 1 here, -1, I'd get 1/4 to the -1st power, which would be 4 to the 1st power. If I plug in 0, I'm going to get 1. Remember, they all share that point in common. And if I plugged in 1, I would get 1/4. And you could do it for 2. 2 would be 1/16. So now that I have my XY table, let's plot those points. So 16 on the x-axis, that's, I can't plot that one. It's off the chart. 1 -4, or 4 -1, I mean, 1 0, 1/4 1. So this is the look it's going to have. And remember, we know that it has that vertical asymptote at the line x equals 0. Both of these do. Let's take a look at the ones that remain here. These are asking us to find the domain. So when you want to find the domain, you are going to take a look at this. And you're going to set whatever is in the argument greater than or equal greater than 0. So let me write that. Take the argument and set it greater than 0 and solve for x. That's how you find the domain. So for this one, I would say 3x minus 1 is greater than 0. I'm going to add 1 to both sides. That will give me 3x is greater than 1. And then I'm going to divide both sides by 3. And I'm going to get x is greater than 1/3. So writing it in interval notation, it would be 1/3 to infinity. The next one, I'm going to take, again, you're looking at this part here, and you're going to say x squared plus 1 is greater than 0. Subtract 1 from both sides. I'll get x squared is greater than -1. I'm going to take the square root of both sides. I'm going to get x is greater than the square root of -1, which that is not a real number. So this must have all real numbers as in the domain. And we can check it. Like if you had plugged in a -10 here and you squared it, you would get 100 plus 1. This overall would be positive. If you had taken a positive 10 and squared it, you would get 100 plus 1 and still positive. So anything you put in here would work. All real numbers. If you end up with a statement where x has got the square root of -1, an imaginary number, then you're going to say all real numbers. The last one here, we have this x minus 2. So we're going to say, let's let x minus 2 be greater than 0. Add 2 to both sides. We'll get x is greater than 2. And so it'll be 2 to infinity. Now be careful when you're solving these inequalities. If you divide or multiply both sides by a negative number, you have to flip that inequality. That didn't happen to any of the examples here. The remaining page is some applications. And so we have, it says here in chemistry, we have the pH of a solution is defined by this function, where H is the hydrogen ion concentration of the solution in moles per liter, and distilled water has a pH of approximately 7. A solution with a pH under 7 is called an acid, and if you're over 7, it's a base. So the gastric juices in your stomach have hydrogen ion concentration of 10 to the -1st moles per liter. Find the pH. So I'm going to write the function from up above. And they have an ion concentration of 10 to the -1st. And we want to find the pH, so I'm going to plug in 10 to the -1st here and put that in my calculator and see what I get. So I'm going to do negative and then log. This is the common base. And then I'm going to say 10 to the -1st power. And I end up with 1. So the gastric juice has a pH of 1, which it is acidic, so we would expect the to have a pH that's more acidic. Tomato juice has a hydrogen concentration of -10 to the -4.1 mole per liter. So it said to find the pH. So we're going to plug in 10 to the -4.1, and let's put that on the calculator and see what we get. So negative log, and then we're going to say 10 caret -4.1. And we end up with this value of 4.1. That's a tomato juice pH. And then let's do the last one. The last one says that milk has the concentration of this, 3 times 10 to the -7, and it wants us to find the pH of milk. So putting 3 times 10 to the -7, this is how you would enter it in the calculator. You have to hit that second comma button for the times 10 portion. And when I hit enter, I get 6.5 as the pH of milk.